Hello, welcome students. This is chapter 13, and what we're covering today is equilibrium. So far we've mainly been talking about reactions as they proceed in a forward direction, and we don't talk about them going backwards from products back to reactants. So the reality is every reaction actually has some possibility, even if it's just extremely negligible, to go in the reverse direction. There's the activation energy to go in a forward reaction and forward direction. It takes a certain energy, and to go back, maybe the hill is harder to climb. So we're going to talk about in this section just reactions that are reversible. And what we're really going to conclude at the end is that they reach some sort of equilibrium state of concentrations that at an equilibrium state, those are pretty much steady. Okay. So basically, let's start out with an example. We have two nitrogen dioxides reacting together, so two of these guys, N is blue, O is red, and when they combine, they can form a new bond, an N-N bond here to generate dinitrogen tetroxide. We could observe this with color. The reactants are brown, the products are colorless. The whole point of using this example is there's a nice equilibrium that occurs. You can go from the two nitrogen dioxides to your dinitrogen tetroxide. But you can also go backwards. You can take your product, and your product can break apart, break this N-N bond, and go back to the reactants. So these are going back and forth. So no matter what state you start at, meaning either all reactants or all products, eventually you'll keep going back and forth, and reach a state where you have the concentration of reactants and products constant over time. So that's what we're going to explore here. So we've got that same reaction occurring, and I'm just going to show this in a plot. Basically, let's say you start out with a ton of reactant, green, high concentration of your reactant, but no product. So the blue, which represents the amount or concentration of product on the y-axis, is at 0. So we start out with a lot of reactant, no product. This is pretty standard how we've been looking at reactions. Over time, you're going to use up your reactant, so this green line will decrease, your reactant concentration will decrease, and you're making product. So the blue line will increase to give you your product. Over time, you reach what's called an equilibrium, where you end up with the steady state or constant concentration of the reactant and products. I'm not saying that these concentrations are equal. You can see that one is below 0.02, one is a little over 0.03, but they're steady over time. So here's an example. Maybe at equilibrium, you don't have equal amounts of these, but maybe you have 3 N2O4 molecules and 4 NO2 molecules. That's just an example. And what that means is at equilibrium, you basically have this sort of concentration, but still you're going in the forward direction and backwards direction, just constantly back and forth, but over time you maintain that amount. So one really important thing to talk about is kind of the rate, basically how fast these are occurring. And if we're going to keep this at a steady amount, then at equilibrium, the forward and reverse rates are equal. Okay, we can describe those concentrations using what's called an equilibrium constant. And this is a very, very important expression here, this equilibrium expression. The reason is you'll go on in Chem 160, in organic chemistry even, to analyze product distribution. So just really take hold of this. The reason why we include this in Chem 150 is so that you guys can really see this early and start applying it. So let's just talk about a general reversible reaction. A plus B gives C plus D, but this double-headed arrow here, or arrow in two directions, shows and emphasizes that this reaction is reversible. So our equilibrium expression is to arrange this so that we have some constant K, and a constant is just some number for this reaction, is the product concentration, so concentration of your products, to their coefficient power. So do you see how the coefficient of product C is little c? So we write the concentration, which is the molarity here in this case, to the little c power. And then big D, the product D, its concentration, molarity, to the little d power, divided by the reactants to their coefficient power. So big A to the little a power, and then big B to the little b power. Okay, this is important for you to write. You guys should be able to be given a reaction that's reversible, and you should be able to provide this for me. These are equilibrium concentrations. So I just want to emphasize here on this next slide that it doesn't matter what concentrations you start out with. At the very end, you'll reach these equilibrium concentrations of products and reactants, and they may not be the same concentrations for each type of experiment that we're going to start with, but what will be the same is the equilibrium constant, which is calculated by looking at those ratios of equilibrium concentrations. Here's my example. I've got 3 different experiments, and I just want to test this out by first saying, oh, for this reaction, nitrogen plus 3 hydrogens give 2 ammonias. If I start out, here's my first experiment, with some amount of reactant but no product, at the end, if I start out with 1 molar each of the reactant, I'll get these equilibrium concentrations. These are kind of just, you can't predict these numbers just straight off. But if I plug that into my equilibrium expression and just crunch those numbers, I get this K value, this KEQ, it's an equilibrium constant, 6.02 times 10 to the minus 2. If I do a different experiment, I start out with no reactants and only product, 1 molar in product. What happens is this goes back and forth. First, the 2 NH3s will react to give and basically decompose to give nitrogen and hydrogen. And these will go back and forth till you reach equilibrium, and you get these equilibrium concentrations, which you couldn't predict straight off. But look at this, they're different. What's the same, however, is if you crunch those numbers, plug them into the equilibrium expression, you get that same constant. So again, if we start out with random numbers for all 3 of these, you get a certain equilibrium concentration, you still get that same K. So this is powerful because if you know K, then you could actually start predicting equilibrium concentrations. Okay, you guys can practice this. This is just really some math to do, but basically you have the same equation, write out the equilibrium expression, and then solve for K. So go ahead and do that. And I'm going to go over that now. You have the same expression, ammonia, the concentration of ammonia to the 2nd power, so squared, divided by the products, so N2 concentration, there's no coefficient, just 1, so it's just that concentration times, be careful, don't write plus, it's times the concentration of H2 to the 3rd power cubed. So then crunch these in your calculator, you should have come up with this number, about 10,000. It's actually 11,000 if we keep with sig figs. Okay, one thing that I want to make sure you understand is when you're writing an equilibrium expression, you don't include solids or liquids. The reason is these are just such vast quantities that they're not really, they don't play a role so much in the equilibrium. So if you have this reaction, calcium carbonate, decomposing to calcium oxide and carbon dioxide gas, the only player in the equilibrium expression is the carbon dioxide because it's in a gas phase. So that'll be the only concentration present in the Kc. And so just to let you know, you can also express these equilibrium concentrations in pressure. For example, if you just have gases, I could have just written the partial pressure of carbon dioxide. When it's looking at concentrations, we call it Kc. Okay, so how do we use Kc? We basically use it to get a feel for, are we going to get mostly reactants or products at equilibrium? This is really important as you're designing experiments, running experiments, predicting what's going to occur. So if the K is really big, just remember what K represents. K is products over reactants. So if K is big, that means you have a lot more products than reactants. So that means mainly products are present at equilibrium. So whatever you start with, if you let that reaction run, let the equilibrium state occur, then you'll observe mainly products. So that's a number big, it's over 1,000. If the K is really small, less than 10 to the minus 3, then that means you mainly have reactants. If it's something in between, then both are present at equilibrium. Okay, let's just practice. Here I have water decomposing into H2 and O2. The Kc is 4 times 10 to the minus 48. That is a teeny, teeny, tiny number. So if that's super, super small, that means you had a lot more in the denominator. So that's where the reactants are. You have a lot more reactants. That means this doesn't want to occur to appreciable extent. If I just let water sit around at this temperature, these can go back and forth and are in equilibrium, but it's mainly going to be reactants. If I flip the equation, so now I have the reactants on the left, and I basically start out making the H2 and O2 the reactants, giving water, that K is favorable. That K is huge. It's times 10 to the 47. So I used extreme cases here, but what that's saying is this will go to an appreciable extent. You'll mainly have product water in that situation. Okay, the last main concept we're going to talk about is Le Chatelier's principle. Some of you may have already learned this in a previous chemistry class. And I'm just going to give you the basics. Your book is going to try to explain this using a lot of equations, a lot of numbers. I don't do that. I do this more qualitatively, and it works very well. What Le Chatelier's principle says, if you apply a stress to a reaction mixture at equilibrium, the net reaction occurs in the direction to relieve that stress. So I already mentioned that a reaction at equilibrium, it's going back and forth. You get this steady state and a constant equilibrium concentration of reactants and products. But what if you mess with that system? What if you like poke that system? You either remove a reactant or add a product, change the temperature. The equilibrium is going to shift to either the left or the right, meaning left is reactants, right is products, and it's going to shift to relieve that stress. Here are examples of stresses: a change in concentration of reactant or product, a change in the pressure or volume that can greatly affect gases, or a change in the temperature. And what you would look at there is whether this is endo or exothermic. So let's just look at these. Let's use this example here. Iron 3 oxide reacting with carbon monoxide to give liquid iron, molten iron, and carbon dioxide. We're going to predict the direction of the reaction when the equilibrium is disturbed by first adding iron 3 oxide. So it may help you to think about the equilibrium expression. Since iron oxide is a solid and this iron is a liquid, they fall out of the equation. So the only major players affecting equilibrium are carbon dioxide and carbon monoxide. So CO2 on the top, CO on the bottom. So adding iron 3 oxide is not going to play a role. So there's going to be no effect in this case. Let's go to the next one, removing carbon dioxide. So these are going back and forth. The reaction direction is going back and forth. The forward and reverse rates are equal. And you have an equilibrium concentration. What if I removed some carbon dioxide? What the reaction wants to do is make it up. So it'll shift the reaction to produce more carbon dioxide. So it shifts it to the right. And so it goes towards product. So you remove carbon dioxide, the reaction shifts to the right. What if you remove carbon monoxide here? If you take away some of this reactant, the reaction wants to shift to make it up. So if you remove some of the carbon dioxide, the reaction shifts to the left. And what I mean by shifts to the left is the reaction will want to go in the left direction. The products will react to give more reactant, more carbon dioxide. So this goes to the left. Okay, let's look at this. N2 plus the H2 giving ammonia. We've seen that. This is actually exothermic. What that means to you is heat is released. It's helpful in this situation to think of heat as a product. So we could put heat on the product side, on the right side, and kind of think of it as a product. So what direction would the reaction shift or go towards if you added heat? This is already exothermic, releasing heat. So if you add more heat, you don't want to continue to release heat. You want to consume heat. So you'll want to shift to the left and use up more heat to relieve that stress of added heat. So this first one, adding heat, the reaction shifts to the left. Or if you add ammonia here, that's a product. If you're adding more of this, you want to get rid of it, so you shift to the left. If you add more N2, you want to get rid of it, so you'll shift to the right. Okay, so I wrote that here, and that's where I want to end today. All right, you guys.